Swayam Prabha. Digital India. Educated India.
So you 6 people went for a party, and then irrespective of who went, who are these 6 people, 3 of them should be mutual strangers, or 3 of them should be mutual friends. Friends means known to each other, non-strangers. So we saw a small proof for that. It was easy, but this problem can be generalized, right? Instead of looking for 3 strangers and 3 friends, mutual friends, mutual strangers, we could have asked for k strangers, k mutual strangers, or k mutual friends. Instead of 3, 4, 5 like that, every pair among them should be friends, or every pair among them. The question then is, how many people should go for the party, right? For this to be a guaranteed fact, right? For this to be guaranteed, how many friends should go for the party then, right? How many people should go for the party? I showed that if 5 people went for the party, then that statement was not correct. 6 people or more should go for the party, then only that is true. But when it is k we are looking for, then we say if r of k persons went for the party, then it's sure that either there are k mutual friends or k mutual strangers. We have to estimate this number. Typically, to get the correct value is difficult. You usually get upper bounds and lower bounds. So we should understand what is the meaning of upper bound and lower bound. Upper bound means, so suppose if I get some number here, some 2 to the power k or something like that, if I put, that means more than 2 to the power k persons go to the party, then irrespective of who are they, what is their relation, I mean between the pairs of people, what kind of relation is there, does not matter. Somewhere in the gang there will be k people who are strangers, mutual strangers. Mutual strangers, every pair among them will be strangers, or every pair among them will be friends, right? So that is the meaning of upper bound. What is the meaning of lower bound? Suppose if I write 2 raised to k by 2 is a lower bound for this. It means you can find some 2 raised to k by 2 people, right? It is not that any 2 raised to k by 2 people there. That means some special type of people with some kind of relations are there, and then you can find such that neither of this thing happens, neither k mutual strangers nor mutual friends. So it's much easier to talk in terms of graphs. So instead of talking about persons, we will say vertices, and then one possible way is to consider the entire graph as a complete graph, and we are coloring it. Yesterday we did it. So if it is a complete graph on so many vertices, we are coloring all edges. So friends corresponds to say red color, and strangers corresponds to green color, and all edges will get either red color or green color. Now you are looking for a k sized green clique or k sized red clique, monochromatic, that is the word, monochromatic clique of k vertices is what we are looking for, right? See, you should remember that in this 2 color case, there is another way of presenting this thing. Instead of putting the color, you can consider that red edges are present edges and green edges are absent edges. That means just think of a graph with only those red edges, right? So now we don't have to talk about complete graph, just talk about a graph, right? In any graph, either there exists a k clique or independent set of cardinality k. That would be much more reasonable in the context of what we were studying all these days, independent set and clique, right? So, not that this is a complementary things, right. Clique is very much like independent set, just that it is exact opposite, two extremes they are, right. So, we are trying to tell that either this one or that one exists, one of the extremes are unavoidable. Both are structured, though in two different ways. So, one of them cannot be avoided is what. So, when there are R of k vertices or more, then we are sure that irrespective of which graph you take, you can try to adjust the edges in whatever way possible and try to beat this statement, but it is not possible. So, if you try to suppress cliques, independent set will come. If you try to suppress independent sets, clique will come. That means, whenever you see a big independent set, try to put an edge there and destroy it, but then when you do destroy all of them, clique will appear somewhere, right. That is what we are saying, right. And then lower bound means, so when I say that 2 raised to k by 2 is a lower bound, that means there exists a graph on 2 raised to k by 2 nodes, at least 2 raised to k by 2 nodes, such that neither a clique on k vertices exists in it, nor a independent set on k vertices exists. These numbers are also big. That is why when working with small graphs, we won't realize this order in the disorder. That is the phrase we use. This order in the disorder. So, when we work with 1000 node graphs or 10,000 node graphs, now you may not see anything very visible there. But when you go to very large number of nodes, literally millions of nodes, when you start seeing this kind of structure, something or the other keep coming. It is not right. So, it is interesting that it will happen. So, mathematically the initial proofs are not that difficult, right, but we will see that. So, but my intention is not to prove the upper bound, which may be more fascinating to you somehow, but you will see that the upper bound is in fact easy. Some upper bounds are easy right here, but the difficulty here is lower bound. It was historically that was more difficult because the initial upper bounds. So, you can also see that if you think for some time, you will also see this lower bound. How do you show something like that exists? That means, on 2 raised to k by 2 vertices, you can have a graph, you can construct a graph avoiding both clique and independent set exists, right. The funny thing is that it looks, oh yes, but 2 raised to k by, what kind of construction will you go? There is a lot of nodes, right. If you, how will you cannot keep drawing it, right. And even if you draw, you will see that this property is very forcing, somewhere or the other it keeps appearing, right. So, it is not so easy to figure out how to do it. So, then Paul Erdos came up with this wonderful idea that we can use probabilistic method to do it, right, which essentially is a very interesting and good idea, that he says you cannot construct it because you are trying to very cleverly do it, but do not be clever at all, right. Just randomly pick a graph from the distribution GNP, which means that, like I told yesterday, take a graph and then for each pair of vertices decide whether there should be an edge or not with probability p, right. So, head should be p, tail should be 1 minus p, right. That was the GNP model, right, GNP distribution, right. The outcomes are all kinds of graphs, and then we know with what probability a particular graph comes, right. It only depends on the number of edges. Now, we can, as a for the initial problem, we fix p equal to half. That means the probability of an edge being present is half, absent is also half, right, with half probability it will be there. Then I told yesterday that the probability of any graph, right, there is no difference in the probability. So, all of them have the same probability, namely 1 by n choose 2, 1 by 2 raised to n choose 2, right. That is the probability of each graph. Now, Now it's just a matter of analyzing and proving that there exists one. It's not that all graphs are like that, right? We only want to show that there exists one, right? So we do this thing. So there is this n equal to 2 raised to k by 2, put n equal to 2 raised to k by 2 vertices, and then draw edges or not draw edges depending on with probability half, right? Decide to put it or not. The first question we ask is naturally, what is the probability that the thing that we do not want exists? That is the usual way to attack probably this kind of thing. So, which is called the probability of a failure, right. So, we should say that failure does not happen, then the success happens, right. The failure here can happen in two different ways. What are the two different ways of failure here? What are the bad things that we do not like to have? One is a clique of cardinality k, that is a bad event for us. If you find a clique of cardinality k, that is bad for that. That will be the first type of failure. The second type of failure is an independent set of cardinality k, right. Both we want to avoid, right. We do not want that failure or this failure, type 1 failure or type 2 failure, we do not want, right. Then we say that it is successful, because if you get a graph without both, then that is exactly what we are looking for, right. Then what we are interested in is the event, the probability of the event that both type of failure does not happen, right. In both cases we have success, that means that also does not happen, this also does not happen. And if that probability is even at least something, what does it mean? Suppose the probability of no type 1 failure and no type 2 failure is greater than 0 means what? What does it mean? If the probability that neither there is a clique nor there is a independent set, that means the probability that the kind of things we are looking for exists, so such a graph comes out of this experiment, right, is greater than 0. What does it mean? If the probability is greater than 0, does it mean that it exists? Can exist only, you are saying. Why can exist? Right? Why this is, I intentionally asked this question, not because I know that this is one issue with this probability. How much ever we teach, we get intuitive, right? See, you remember the probability is greater than 0 means it is not what is in your mind. I told we are doing only mathematics. Yesterday we set up all the machinery for that, right? So therefore, this essentially our distribution is a set of outcomes and the probability values associated with it. And the event is no event, right? It is not like something which is happening or something. It is essentially some subset of outcomes, right? Outcome is graphs here, right? Which is how many possible outcomes are there? 2 raised to n choose 2 outcomes are there, because those many graphs are possible, right? Each outcome is assigned a probability. In this case, all are equal probabilities, namely 1 by 2 to the power n choose 2, because all are equal probabilities, uniform distribution it is. So now the probability of this event means the events means those kind of graphs, right, which does not have clique, does not have independent set of the type we are looking for, that means k sized. If the probability of this has to be greater than 0, at least one graph should be there like that, otherwise how can that event be greater than 0? If there was no graph of that sort, then we know the probability of that event will be summing up the probabilities assigned to those outcomes corresponding to that event, right. If there was no one, it would have been 0, right. So if it is greater than 0, at least one should be there. So there is no magic, there is no intuition, there is nothing like that. It is just from the basic principles, because we started from this, idea that these are the outcomes and each outcome has a probability value, and then we are just when we show that some event has a probability greater than 0, actually it means there are certain outcomes which correspond to that event, and the sum of those probabilities assigned to those outcomes is greater than 0 is what we are saying, right, because if nothing was there then it would not have added up to more than 0. So, therefore, that is enough to show this probability of this thing is greater than 0, right. But how do we show that the probability of this thing is greater than 0? See, sorry for my, see I am very bad at writing all these things. This is what we want to type 2 is greater than 0 is what we want to show, right. This thing is, we know that this stuff, right, is 1 minus probability of type 1 or type 2 happens, right, isn't it, because either this or this happens, it is a complement of that. So, we want this to be greater than 0, that means probability of type 1 or type 2 should be less than 0, this is what we want, sorry, less than 1, sorry, this is what we want, less than 1. Okay. So, instead of asking for whether the probability of both the type of event does not happen is together is simultaneously does not happen is greater than 0, we will say the probability that either this happens or the other thing happens is less than 0. So, because once you ask that, there is an advantage, probability that type 1 or type 2 event happens is less than 1 is what I want to prove. So, instead of this I can ask what is this thing. Because if the answer for the second question is yes, the answer for the first question is also yes, not the other way, because probability of type 1 or type 2 is at most less than equal to sum of that, no? Because A or B, two events are there, either this or this happens. If we just simply can add up that, and that will upper bound it. Typically it can be less, because there can be some intersection in the set of events, and then it can be less, but then those things are difficult for us. You will also see that when we do most of these probabilistic calculations, we are just discarding many things, right, to make things easy, right. We will freely discard things at intersection and things like that, because keep loosely calculate things, that makes life very easy, right. And the only thing is you should keep track of the implications. That means what we want is this, the probability of this or this is at most 1, but that can still be got if I can prove that the sum of the probabilities of the two events is at most 1, because one side implication. If the second one is true, this first one is also true, right. Agreed? Any doubt on that? Okay. And then, do you agree with me that both events should have the same probability? Because let us look at the probability that the first type of events, probability of type 1 happening. That means there exists a clique of cardinality 1, sorry, cardinality k. So, how do we do that? First, we can see that can happen in various places, right. There are n vertices. Let us number the vertices from 1 to n. So, it can be on the first k vertices, or maybe 2 to k plus 1, that numbered vertices, or maybe vertex number 10 to vertex number k plus 10, or not necessarily consecutive, 10th vertex, 20th vertex, and k times 10th vertex, right. So, many possibilities are there. How many possibilities are there? there are exactly n choose k possible places the clique possible ways in which this k cliques can come. Okay, let us fix one of them for the time being, but that would make our life much easier, and then say 1 to k suppose. What is the probability that on that set of vertices we will have a clique? Half power k choose 2, because there are k choose 2 edges among those vertices. Is it clear to all of you? K choose 2 edges among those. So, all those edges should appear, and that appears with half probability, right. So, half power k choose 2. There are edges outside that set we do not care about, it may come or may not come, both are okay for us, right. So, this is the probability for a clique to appear in the set of vertices 1, 2, 3, 4 up to k, or like that any fixed k vertices is the thing. Now, can I say that the probability that type 1 event occurs is exactly half raised to k choose 2? Is it correct? No, it is not true, because there are various possible ways of happening now. Now, what should I do to get it the total probability of that type 1 event to happen? That means either a clique happens somewhere. Can I add up all these things over n choose k things? Yes or no? Now, if you add up, you will get much more than the probability. Why? Because suppose there was this thing, okay, there was some intersection suppose, right. So, the probability that there is a clique here and the probability that there is a clique here, right. If suppose there is already a clique here, there is a much higher probability that this is also a clique, because you need a few more edges only, right, because I know that this much is already a clique, right. When for instance, if the two places we are looking, this is 1 to k and this k plus 1 to 2 k, then yes, I mean the probability that there is a clique here, sorry, not like that, that is independent, but no. So, the actually it is not mutually exclusive, right, because if a clique is happening here, then you can it is possible to have a clique in the other things also, right. So, there is a lot of confusion there, right. So, therefore, you cannot simply say that because there is a clique here these two cliques can come together also, right. There are graphs where these two cliques are coexisting, right, there is something in the intersection. So, therefore, yeah, if when you find the union, you may have to minus that intersection part, right, but as I told you earlier, that and all a headache, right. We cannot do all those things in this entire probabilistic method. Whenever do the calculation, we will not take up any work which gives us headache. We will keep going the easiest way by bounding, because we are somehow confident that if we get we will get things are all very loose, right. So, what I do is I just simply add up, right, that will give you an upper bound, right, is it correct? So, for E I just put it n choose k into half raised to k choose 2, sorry. So, this 1 by 2 to the power k choose 2 was the probability that in one specific set of k vertices has a clique in it. There are n choose k possible things. If I sum up all of them, I get something much more than the actual probability, but it is an upper bound, right. So, I take at most that, because what I am interested in the sum of probability the type 1 event and probability of type 2 event, and that was I wanted it to be less than 1, but now I took a much bigger number than that, and then if I add up those two bigger numbers and still less than 1. So, the earlier one I was looking for also will be less than 1, right, because I will just ask for a looser thing, namely if I get n choose k into half raised to k choose 2 plus n choose k into half raised to k choose 2. If this itself is less than 1, the probability of type 1 event plus probability of type 2 event also will be less than 1, and then probability of type 1 union probability of type 2 also will be less than 1, right. though I am loosely bounding, going bigger and bigger numbers, and I want it to be less than 1, right. So, you may wonder why I took for both type 1 and type 2, I took the same numbers. Why? Same upper bound. Because it's the same thing, because we put probability of edge present is half, also absent is half, right. Instead of the clique, I wanted independent set, that is the same calculation, right. Because all the edge should be absent there, k choose 2 edges should be absent, that means half raised to k choose 2, and there again n choose k possible places this independent set may come, that is why the same thing, right. So, that is all very simple things. So, therefore, you just have to show that if you add up these two things, it will be less than 1, right. So, that means 2 times, you have to show that 2 times n choose k into half raised to k choose 2 is less than 1 is what we should show, right. If you show this thing, everything earlier will be as we wanted, less than 1, and the first one should be greater than 0, right. So, we were looking for looser and looser inequalities. So, if you are unlucky, all these things will not work. Maybe the first thing may be still correct, but if you put a bigger number, maybe it might not work. So, that's not a way to infer that if this is not working, that will not work, we cannot say. We can only say that if this works, that also works, right. Luckily, if this will work, right. So, I use the word luckily, right. So, because if you really wanted to compute all those carefully, then we will never reach this far, because those calculations will be very tough. So, that is the good and easy thing about it, just put union bound, that means it is called union bound, sum up, right. Then there are several events and you want the probability of the union of those events. Do not bother about what is how much is common to them and all, just sum up, right. Now, so now let me do some calculation for you. So, this 2 into what is this n choose k, n into n minus 1. So, there are k terms, right, n minus k plus 1 up divided by k factorial here, am I right, 1 by 2 into k minus 1 by 2. Now, the upper part, this portion I will replace by n to the power k, that is fine. Because why that is fine? Because I am looking for this entire thing to be less than 1, and I am again doing my trick of being very liberal, right. Just take the upper bound. If that is less than 1, this will definitely be less than 1. I take a bigger number, that is all, n raised to k, because I cannot, I am, I look at this n into n minus 1 into n minus 2 itself, I get scared, right, because it is very difficult to manipulate that. So, I just go the easy route and take n to the power k, and below what will I do? K to the power k factorial. So, I want to put 2 raised to k here. See, what can I put below? Below I should put a smaller number, so that the entire thing goes up bigger, right. Then we can still say that if after the replacement it is still less than 1, this will be less than 1. But is it true that k factorial is always greater than or equal to 2 raised to k? For k equal to 1, it is not true, but we do not care, because we will assume k is a little big. K equal to 2, is it correct? 2 factorial? No, still not correct. K equal to 3 factorial, 6 is greater than, no, 4. Correct now, 4. $32, right? 2 raised to 4? 16. Okay. It's small now. Okay, this is 16 and this is 24. Right? Earlier it was not, because 3 factorial was 6 greater than equal to, oh no, this was also correct then, sorry, this was not correct. This is correct, right? From now on it will be correct, because it will k factorial will grow faster now. Every time you are multiplying by k, here only multiplying by 2, right? So from k equal to 4 onwards it is correct. I am claiming that no, I can assume that k greater than equal to 4, because k equal to 3 case I had done already, right? 6 I had seen, k equal to 3, r of k is equal to 6, then r of k is equal to 6, and that was definitely bigger than 2 raised to k by 2, 3 by 2, 2.15. So that was okay, that was a handled case, already tackled case. So therefore we can assume that k greater than equal to 4. Therefore I put 2 raised to k below, and then it will so happen that this will be n raised to k divided by 2 raised to k, and yeah, 1 by 2 raised to k into k minus 1 by 2 here, right. If this is less than 1, everything else whatever I wrote previously was less than 1, right, because I took bigger ones here. And n, I know my aim is to put, right, n as 2 raised to k by 2. I will just put 2 raised to k by 2 here, right. That means 2 raised to k square by 2 raised to k, and 1 by 2 raised to k square by 2 minus k by 2, right. I want to check for the n equal to 2 raised to k by 2 whether this is working or not, right. And then what all things will happen, this will cancel, and 2 raised to k minus 2 raised to, and 2 raised to k minus 2. So finally this will turn out to be 1 by 2 raised to k by 2 is less than 1 is what we want. And I already assumed k greater than equal to 4. This is only requiring that 1 by 2 raised to 4 by 2 is 2, right. It definitely less than 1, not actually not less than 1, less than it is less than 1 by 4, right, isn't it? Okay, sorry, less than equal to 1 by 4, less than 1 by 2. 2 term is there. There was a 2 term earlier also. Okay, 2 into n choose k into, yeah. So that 2 term would take care of, sorry, here everywhere there was a 2 term multiplier, sorry, yeah. So this was less than, so okay, so 1 by 2. So into somewhere we are putting, yeah, because in many places we have already put bigger, strictly bigger value, therefore it's okay.